Hello everyone to this week's optimization class. So today we're going to discuss on duality, which is an important concept in optimization, especially in convex optimization. And then in the middle part we will discuss some interesting methods we can apply without any gradients, if you do not have access to gradients. That's so-called gradient-free optimization. And finally, we'll discuss some applications in deep learning algorithms to train neural networks in particular, where we can discuss a few of the recent methods which are modifications of stochastic gradient descent, in particular things like AdaGrad and Adam, and discuss a bit the idea behind those. So let's get started. Duality is the first part. Now, this is maybe a bit abstract if you see it the first time, but I'm sure you have seen quite a few examples of duality in other contexts, like in math classes. So there's always often a duality between classes of different concepts, and here this is for functions. So what we look at is the concept of a standard convex function, like here, and the special thing is here that we consider functions which go from just the variables, they go to a number, and that number can be also, it's kind of the augmented version that you can also answer that plus infinity, which is kind of a special case. So instead of saying the function is not defined there, you can say, yeah, it's plus infinity. So this is a very important class of functions. So if you have a function which is given to you, then you can look at its dual or its conjugate function, and that's what's denoted here as a f star. And so here is a visualization of that. So or the definition better is that it's kind of a maximum of a linear form minus the original function. So think of the original function was living in the space where you had x as your variable, which was here, and now your dual function takes an argument y, and that's just defined by the maximum of the original function plus kind of a linear form. So that sounds pretty strange, so why would this be a good idea to do that, and what's the relation of the two? So for that we look at a picture to understand a bit better, and it's still abstract, so I apologize in advance. So it's not very intuitive to have this definition of the dual, but again, so what we just said in a formula already, let's also let's define this in the picture. And okay, maybe not able to use the same colors, but here you had this is your f. Now so here you're at f of x, for example. So fine, and now how do you get to f star of y? And the way that works is that you look at the slope, which is defined on this picture here. So here you have the slope for any given y, right? So for any value y, you now want to figure out what is the value of my dual function at the point y. So this is what you have at the bottom here. So we want to find out what is this f star of y, so given any y. How does this work? So it turns out, if you just draw in the picture the formula we have defined above, then this is what you get. You get that the value f of y is actually defined by this point here, so that the vertical component of that point, that is exactly the dual function value, or the value of the conjugate function for the given y. Again, y is the slope of this green line. So this thing here, trying to visualize it, this is the length of that thing, that is f star of y. All right. And how does this make sense? Not so clear from the picture yet, and it's also maybe even more annoying to then visualize this if you're not in one dimension. So this is just a one-dimensional example. But if you have then d-dimensional. But the crucial point I want you to take away is that this is always taking the inner product, so this kind of linear form. This is how the two type of variables are connected, right? So now we have, if you have more than one variable, then you have like x in d dimensions and y in d dimensions. And how they are related is exactly through the inner product. So that's why we have this here, and that's also that's going to then generalize here what we have instead of a line. If you're in more than one dimension, then you will just have the plane, which is defined by y, and again you kind of have the same pictures here, that the dual function will be the vertical component of that thing. Okay, so this is called the conjugate or Fenchel conjugate of the original function, and let's see what we can do with that. One important property is that this is actually a convex function. So this we actually have here on the next slide. So that's kind of interesting. So that this thing is a convex function no matter if the original function was convex or not. So here is your f, then here is your f star, and why is that? So that's kind of interesting. So if you look back, then here's the definition. So why is that giving you convexity? So the nice thing here is that this is a maximum of many functions in y, right? So this whole thing is a function in y. So if you think about this way, then you have here f star, plot this, right? And then here you have y. So you have many functions depending on y, and they all happen to be linear functions because f of x does not depend on y. So the only thing depending on y is this x times y, the yellow linear term. So what you basically have is a lot of linear functions, and then what happens is that the f star of y is defined to be the maximum of all of those. So then you have each of these purple lines is corresponding to a particular x. You have infinitely many of these x's, but it's not going to matter for our argument here. So what we have here is that the maximum of all these functions, that's what you get here. This is called the upper envelope of all these lines, for example. And it turns out that the maximum of many linear functions is actually a convex function. So the orange thing is the graph of my f star. So that thing is a convex function, no matter what the original f was as a function. This is interesting, and that's what we have written here on the first line. So okay, and you can see here it's written down what I just said, that because the maximum of affine functions or linear functions is maximum is convex. That's one thing to keep in mind. It's going to be very useful. Another thing is the Fenchel inequality, which is also basically the core property of this whole concept, and this is like the main thing which will allow you to relate the two f and f star together. So what's their connection? That's the differential inequality. And that's written here. So what it says is just that the sum of so your conjugate function at y and the original function at x, so that thing together is always bigger than this linear term. It can be equal, but it's always at least as big. This is differential inequality, and we're going to use this in a second to understand a bit better how these things relate. So one thing which is interesting is that you can take this conjugate, of course, as many times as you want. So if you take the conjugate of f, so you go from like, here's f, then you take its conjugate, star, and then you take the conjugate of f star again, why not? Then let's visualize what this means here. So, and let's, for example, think that this f here originally was a non-convex thing. And then what's interesting is that the conjugate is convex. And then the conjugate of the conjugate, of course, is again convex. So that's because we're using the first property here. So maybe something like this. I don't know exactly how it would look like in this particular example, but I know that the double conjugate is certainly a convex function, and that will actually be very related. This guy will be very related to the original function f. It's kind of the envelope of the original function. So this was non-convex, then the conjugate is convex. And again, this guy is again convex. All right. And why is that? So we should better prove what we claim here. So this is pretty clear that it's convex because we just proved it before, and if you do it twice, it's still going to be convex, so that's clear. What I want to discuss briefly is this property here, that it's also the case that it's lower than the original f. So that the double conjugate is kind of a lower bound of the original f. So that guy is like your double conjugate, say. And that guy, if you would want to plot it here in the same picture, it's always below the original f, and it makes that original f convex. So that's why it's the kind of convex envelope. And why do you get this? Of course, this is directly from the differential inequality. You take the inequality, so f of x plus f star y, and then you again add f of x. So so now you add the double conjugate of x Okay, so this thing, you know, is at least x times y. And so, and now you want to compare this to relate this to f, and then I will just use the definition here of the, well, okay. Here I will use the definition. So what's the double conjugate? I will just use the definition of the conjugate. So which is here. So maybe I first write times xy minus f, the original function of y in this case. So, and then when I combine these two, it will be clear that the sum of these guys together is smaller than the original f. Okay, there's some more properties. So this one we just proved, and so now, and again, as you saw, we just use it to prove it using Fench's inequality. So if you do this again, and ask in the proof that we just saw, if you look at Fench's inequality, you ask when is it actually an equality. So then you can be even more precise on when this happens, and then you will see that if the original f is already closed and convex, then you get a precise equality. That is pretty nice. And again, to interpret this a bit more broadly, basically what you have seen from the picture would already indicate to you that this is very closely related to the definition of a subgradient, because we always talk about these linear forms, which are actually tangential to the functions. So that's, or they're always below the function, and that's very, very closely related to a subgradient. So the definition of what a subgradient is. And this is actually also super useful with the convex conjugate, so which you can see here. So you see this concept of cut subgradients also directly allows you to relate this Fenchel inequality or equality, and to relate the f to the conjugate. In which sense? So that's super elegant in the sense that you have that, if you are a subgradient of f at x, then it's exactly the same thing, and that x is a subgradient of the conjugate at y. This is an equivalence. So this is nice, and this tells you beautiful symmetry between the conjugate and its original function. And also that this will happen exactly if the Fenchel inequality is an equality. So that you have here. So, and this is the exercise for you this week. So we don't have much exercises because you surely are interested to work on the projects. And so, but this one will help you to play around a bit more with this concept here. So I highly recommend doing this one. And it's always easier to assume that the function is closed to make this argument. Again, to prove this, you will use the basic properties of maximum of functions, and we actually have a hint for you how to solve this exercise in the exercise sheet. Okay, so we're almost done with the properties. So we discussed everything already. So the very last one I want to discuss about conjugates is this one here. Basically this is saying the conjugate of a sum. Is it the sum of conjugates? And basically the answer is no. But there is kind of a nice property here. So the conjugate is the conjugate of the sum is the sum of the conjugates, but only if things are separable. And so this is basically what is explained here. So if you have a function which depends on two different variables, so function depends on u and function depends on v, well, this is just a name. This can be one big vector of variables. It doesn't matter. But the point here is this separability, which I mentioned. So if the function is such that its first part is only depending on u, and then it's plus something which only depends on v, then you have this particular structure. And if you have that, then the conjugate of this function is very easy to compute. It's actually the sum of the original conjugates. So now the original variable. So let me shed a bit more light on this. So this uv, this was like your original x variable, but it's now partitioned into two parts. So it's a big vector. First part is called u, second part is called v. And this thing here is your conjugate variable, or the dual variable, so to say. Lives in the same dimension, in d dimensions. And again, it's partitioned into two parts. So, and they are actually the same dimension. So if you want to visualize this here, you can think that here at u and v in your original x vector, and now you have w and z. So this thing is in RD. Okay, so this is a property. So yeah, sometimes you can obtain the conjugate of a sum, but only if the function is separable in this sense. Okay, this was a bit dry, maybe a bit abstract with this conjugate, so let's see what this is really useful for. And so to do this, we need one or two important classes of functions which you can then use. And one of the most important classes of functions you can have, which you talk about here, is the so-called indicator functions of a set. So when you have a set, then there's a super kind of natural function which is associated with it, and that's the indicator function. It's super easy. It's just it's here, right? It's just so here. Let's say on the x-axis you have your. Here is my set. The set is called C. Now there's a function associated with this. So this is this axis here is RD. Let's say the set C is a subset of this space. Then the function I associate with that is just that's the so-called indicator function. It's plus infinity if you're outside the set. So you're up here, and then as soon as you're inside the set or on the boundary, then you get 0, and then when you're outside again, then the function is again plus infinity. This is the indicator function of a set. I think you might have seen it before. And what can we do with this? So it's very natural for taking conjugates, because the conjugate of such an indicator function has a very simple structure that's here, and that is called, so what this here is, if you look at it, it's just taking the maximum of a linear function over the set. Maybe if you have seen linear programming, then this is particularly natural to you. So maybe your set C looks something like this, I don't know. Yeah, maybe here I took a convex set, but doesn't matter in general. Okay, what's happening here is that so this maximizing the linear form here. So you're given a direction y, and you're asking which point in the set y has the highest inner product with the direction y. So maybe the origin is here, it doesn't matter so much. And so that's what the support function is. Given a set, give me any direction, the direction is called y. What is the maximum value you can go in that direction in the set, so that you get the highest inner product. That's exactly what you have seen in the Frank-Wolf algorithm, actually. You got the gradient direction, and then you asked, how can I have the highest inner product with my negative gradient? So that's what Frank-Wolf did in one of the steps. So that's finding that point. That's the problem which is called the support function. And the support function then, its value is just the value of this, like, so how big is this maximum? It's not the argmax which you've used in Frank-Wolf, but it's the value. So how big is this inner product? All right, so what do we have? We have support functions, and we have indicator functions, and they are dual to each other. It's kind of nice. Okay, this we're going to use in a second when we talk about interesting applications where we can use the dual. So you might have seen some of them already. Before we get there, I give you one more very nice class of functions for which we understand what the dual is, what the conjugate is, and that's norms. So if you have a norm, so what's its dual? What's its conjugate? That's here. So the conjugate of a norm is something super simple. It looks a bit strange here. It's just an indicator function of the dual norm. So, or if you want to be very precise, it's the indicator function of the dual norm Bob. So the dual norm, every norm has a dual norm. So for example, the L1 norm, its dual is the L infinity norm, right? L1, sum of absolute values. L infinity is the maximum absolute value of a vector. These two norms are dual to each other. So what we have here is that, so then you can ask, what's the conjugate of the L1 norm, for example? If f is the L1 norm, if you want to do that, then you can ask what is its conjugate function. The conjugate function will be the indicator function of the dual norm ball, so that would here mean infinity norm smaller 1. So it's a conjugate function of that set. And so that's something quite convenient. So here this is the indicator function. All right. And yeah, if you want a general definition of what a dual norm is, then that's also written here. But maybe the very most common ones are really L1 and L infinity, and of course L2, and then the dual norm of the L2 norm is actually itself. So which is also interesting if you want to think about that. You can use this example to verify you understand the definition here and verify the property. And again, so if you have norms, it's very easy for us to compute the dual function, or the conjugate function, sorry. All right, so what is this useful for? And maybe one of the very interesting classes where we can apply this duality to have some practical use is generalized linear models. Sounds again a bit abstract, but it's actually really common in practice. So I'll get back to this later, but generalized linear models are linear classifiers, linear regression. So they're extremely common. So you can have this with or without regularization. So I'm sure you have seen this. You also have seen maybe the lasso, which is a special type of linear regression or least squares regression. You have seen there can be different types of regularizers. You have seen support vector machines. So all these are special cases of this exact formulation here. The formulation works like this. So you have a data matrix A. So A is a gigantic matrix which collects all the data points and their features. So the rows and columns are data points or features. So, and you have to be careful which one you want, but this is, we're gonna get back to this. So that is the beauty of duality, that this will be kind of interchangeable, what that either you can formulate your problem as a, here you have like, you always take a linear combination of the columns of your data. So here, for example, if your columns are featured, then you take a linear combination of these features. And once we understand what the dual is, we will see that in the dual we will get the A transpose matrix, and we will get combinations of columns of that. So then we have combinations of data points, and this is quite useful. So we're gonna see how this is related. So maybe you have a ton of features and not so many data points, or maybe it's the other way around, and that's exactly what's going to be interesting here, that we can understand this jointly and have a symmetry between data points and features. And you already start seeing a bit of this now. So here you see you can, let's say the W is maybe can be, for example, your weight vector, if you want to think of a classifier or so. And then you can already see these two things here. Then you have this weight vector has n variables, and the other variable, the x variable, has d variables. So now you're going to think of, so do I have n data points and d variables or d features, or the other way around? And I'm telling you, both is okay. You can have this both way. It will be symmetric, as we will see in a second, and both of it will lead to the same solution. We're actually going to show this. Okay, so far nothing has happened. So here, what have we done? We've just taken this very general formulation, f of the data ax plus g. So the data term is usually, that's kind of the loss term. You're trying to fit the data. So think of f as the fit, data fit, or the loss function. And think of g as the regularizer. So sometimes you also want your model, which is your x. You also want that to be small. Okay, this problem is completely equivalent to the one I have written here. I just introduced a new variable which I call w, and that is exactly defined to be ax. Nothing has happened. I just introduced a new variable. All right, and what are we going to do next? So we're going to, now we have an equality constraint, which is always a bit nasty, but in this case it's going to be okay, because this is a linear constraint which relates our original variable x to the new variable w. So it's going to be quite easy to deal with it, and this is actually, because it's linear, this is where the relation to the conjugates will come from, but let's see what will happen. So what we do is we take the Lagrange dual. So we don't only have one equality here, because this is a vector. W is a vector, so you have many rows in the A matrix. So you have as many constraints as you have here. So as many equality constraints. So for each equality constraint, we introduce a slack variable, or kind of a Lagrange multiplier. And that's exactly what you will get here. So the u here, that is the Lagrange multiplier. And here you keep your constraint, so you write it as a difference that you want it to be 0, but it's not, so you have the Lagrange multiplier. Alright, so nothing has happened here, but except that now we have the Lagrangian formulation, where we kind of still have to figure out how to find u. So we usually, we're going to find the best u in a second, but before we do that, we want to understand what does this all have to do with the conjugates. So we're still like minimizing over x and w, because that's what we originally wanted to do. And now the interesting thing is, because we have this linear form here now, it turns out just by looking at this expression, you see that what's written here are exactly the conjugates of f and g. And that's quite convenient. So let's try to understand this a bit better. So I have the minimization over x, and so what's happening with x here? So there is the g term x, and then there is this term minus ax times u. So that's all the stuff which depends on x, and what that is actually, if you look at it, you see this is directly the definition of the conjugate of g. The question is just at which point. So it's a bit strange, you have this u and a and x. So if you take the a and u together, then a times u is just a vector. Don't worry about the transposes for a second. So AU is a vector, and that vector could also be called whatever it is. And that vector is where the conjugate is defined. So this G conjugate at that point. So that's why here we have AU. So the yellow parts all together, minimizing x over the yellow parts, that's the definition of the conjugate of G. And at which point is it taken? It's taken at U transpose times A, which is a row vector, but let's say we just, for convenience, write this as a column vector, and that's actually why we get A times U, A transpose times U. Okay, maybe you're going to be confused with the A here, so I'm going to repeat the exercise. For the W part, that one is actually a bit easier, and that will give us the conjugate of F. So let's see which parts do depend on W. So that's quite easy. So it's these two parts, the F part of course, and then also the U times W. And that is now super easy to see. This is really precisely the definition of the conjugate of X, except that we have a plus here, but we should have a minus, right? Then it would be the conjugate. But this is trivial to solve because you just say, okay, if I ask what's the conjugate at minus U, then you will put minus U here, and then you actually have the plus. So this, the blue stuff, is precisely the conjugate of F taken at minus U, and the yellow stuff is precisely the conjugate of G taken at A times U. And there is a minus because so now I ask you have to explain the minus outside here, and that's because the conjugate definition was a max, not a min. So let me just for reference put again what the conjugate definition is. Conjugate of Y is defined to be the max, x times y minus f of x. And, okay, this is minus the mean of minus this stuff. If you want to have a minimum instead of a maximum, just a little trick. Okay, so we're done. We have found the so-called dual formulation of this original big thing. So let's write this down. So this is called the original problem, or so-called the primal problem. And now this thing here is the dual. If we then also maximize or properly, maximize this over U, and I'm gonna explain that in a second. But what's interesting here is that the data matrix now originally was the A, so it was like the columns of A were multiplied with your original variables X. Now in the dual, the data matrix has moved into the G part, and it's multiplied not with X, because you cannot, because it's a transpose. So it's multiplied with the dual variable. So the A has how many rows and columns? So A has D columns, because that's what X is. And then that means A has n rows. That means the U also has lives in dimension n. And that's going to be useful for us. So here is the summary. If you solve the dual problem, that means you have to find the Lagrange multiplier which maximizes the stuff in the middle. It maximizes this minimum here. So that is the dual problem, which you directly get from Lagrange duality. That's what we have done. And now if you look at this, then what I said before, and maybe it's more clear here, is that what happened to the data matrix. So I'm going to repeat what I said. So here you had X was in D dimension. It's written here. I don't need to write it. So X in D dimensions. So you had A times X. So that's your primal problem. And now if you look at the dual, then you have not d dimensions, d variables, but now we have n variables, and that's what's going to be multiplied by A transpose. Okay, so what's interesting here is that maybe sometimes the original primal formulation might be easier to solve, and sometimes the dual formulation might be easier to solve. Because one measure of complexity is the number of variables you have to deal with. It's not the only measure of complexity. The other thing is how do I quickly get a gradient, or depending on which method you apply to solve these problems. But it's a very nice kind of symmetry between these problems. And you have already seen this maybe in the machine learning course, where you see that for actually a ridge regression, for example, is usually the easiest example of some of these problems. You have seen that the ridge regression problem has a dual, and that's actually, here you actually see the general, most general duality, which explains this for all these type of problems, not only ridge regression, but also support vector machines, where you can solve the dual a bit more easily. The nice thing here is that f and g here can be quite general, right? It's not that the f always needs to be a particular form, and the g actually can be quite general as well. It can be a non-smooth function, for example. The regularizer can be the L1 norm, it can be the L2 norm, it could even be a box constraint, and that's what you had in the support vector machine, that then the dual was kind of becoming an interval constraint. And that's exactly why, because you have the conjugates which appear, and you have seen that the conjugate behaves how I showed you for the interesting case of indicator function of sets. So that's how you can understand what the dual is of linear regression and also linear classifiers such as support vector machines. So here is an example. A very important problem is the lasso problem, which is used a lot in signal processing. So this is a direct application of what we've just seen. So you have the least squares kind of data term, which is depending on the data AX, and then you have the regularizer term G, which depends directly on X. Here that's just the L1 norm, and then you also have a trade-off parameter if you want. So that's called the regularization parameter, which you have to choose. Okay, so now we have this particular f and g, so it's super easy for us to compute the conjugates, well, if we know the conjugates of these functions, and this is not very complicated. So the square norm is actually self-conjugate, so the squared Euclidean norm is the conjugate of itself. Now the only issue is that here it's shifted by some offset, and then, but you have to believe me at the moment that you can also compute the conjugate of the square norm with shift. Here is what it is. And then for the L1 norm, we can just use what we discussed before. We know that conjugates of norms are easy, so we can directly plug that in. So conjugate of norm is the indicator function of the dual norm. We know what the dual norm is of the L1 norm, it's the L infinity norm. So we just plug that in. And then the only slight problem here is that there is a lambda, so there's kind of a scaling by a constant. So what is the conjugate of something scaled with the constant? It turns out that's the conjugate of the same function, but taken at the scaling inverted. So you have the conjugate of your function, that's the I here outside, but because we ask about the conjugate of a scaled thing, we actually have to scale the argument here by 1 over lambda. That's another trick about conjugates, which is very easy to verify. If you see the definition of the conjugate, you can verify that what happens. Let me try to figure out what's the conjugate of lambda times f. So that's something for you to think about as well, but it's very easy. So if you have this, then we're done. So now we have the dual problem of the lasso. Here it is. So that's general form. We just need to plug in what we just said. We know what F star is, we know what the G star is, we just plug that in. So what it means is I need to take G star at the data transposed. So that's here. So data transposed times U. And also I need to do the scaling. We said that's the indicator function of the dual norm 1. So that's why it means the data transposed times U is smaller than 1 in the infinity norm. So that's the conjugate of G. You must satisfy that, otherwise you are not defined or you're plus infinity. So that's what the indicator function is. So that's why we can write the same thing as a constraint. Okay, so we know what the infinity norm is. Absolute value is bounded by 1, which now we just take the lambda to the other side. So of course, absolute value being smaller than 1 is the same as the data times U having infinity norm smaller than lambda. All right, so this is the dual problem of the lasso, and it's quite simple, the form here, but it's not so trivial to solve this. So what you can see is this is basically b minus u, where it doesn't matter if you have plus or minus here, what it means, because you could have you can replace u by minus u. U is taken over the entire space, so if you call your variable plus u or minus u, I don't care. If you have b minus u, then that means you're looking the point which is closest to b. You're trying to minimize the closest Euclidean distance to the fixed point b. So b is given to you. B is the right-hand side of your data. It's given by the user. It's fixed. Now you're trying to find this u closest to b, but you have a constraint. And the constraint is that data times u must be smaller than lambda in infinity norm. So you're kind of restricted to this infinity norm. It's not an infinity ball because there is the data in front of it that makes it a strange geometric object. It actually makes it a nice polytope. So u has to be in that polytope, and u is trying to be as close as possible to b. And this is a nice example of how the L1 norm is dual to the infinity norm. Okay, in terms of solvers, so the state-of-the-art solvers for lasso, they're actually basically coordinate descent, which you know applied to here. You always just solve the primal problem. So that's practically the most used algorithm. It's also what's implemented in the statistics packages in like R, and also in Python, in scikit-learn and so on. This is super fast. You just change one coordinate at a time, and then you optimize this one coordinate. That's easy. Another way to solve this problem here is by full gradient descent, which you have also already seen. If you apply the proximal operator here, because you have seen that proximal extensions of gradient descent can be used if you know what this prox operator is. But for L1, it turns out we can have this proximal operator, but the coordinate step is just still much cheaper than such a full gradient step, so usually a bit faster. How to solve the dual problem? That's less clear. So this is harder to do because you always have to get back to this constraint, and it's not clear to how to project onto this constraint. Nevertheless, what's interesting, of course, in this primal and dual problem is that the solution is basically the same. So the value of the optimum is, of course, the same for both. That's an important result. And also where it's attained, so if you have the optimal u, it will be easy for you to go to the optimal x, because they're just related with A, the data matrix. Okay, lasso problem is important, but I am not going to spend more time on this. But here is what I said about the two problems relate very closely, that the dual problem and the primal problem are solving the same thing, kind of. If you can solve one of them, you have solved both. This is actually realized or visualized on this slide here. And something which is even more important is that even if you have not solved them completely, this duality will always give you a practical certificate of how good you are already. So you're not there at the optimum, right? But you don't need to. We only want to approximate things anyway. So if you're somewhere at x bar, whatever, it's not the optimum, but it's just some x bar which you got from your solver. It's hopefully a good one, but not perfect. So how good is it? What you can do is you can look at any dual point u, and you just know that the value of this dual problem is actually always lower than, so here is the value of the dual problem. That is always worse, of course, than the best solution to the dual problem, which is the line in the middle. So we don't know the max, right? We don't know the perfect optimum of the dual. We also don't know the perfect optimum of the primal, but we know that they must be between the stuff that we currently have. So in practice, we have this x bar, which is our approximation. We have any u bar. You can put anything there. You don't have to be super creative. So for any u bar you choose, maybe you just choose a random one, or maybe you have an approximate solver which gives you a dual point, which it thinks it's a good one. Whatever you put, you will know that this term here is smaller than, and your optimum, which is like f star, is in between here. So this is f star. Sorry. So the minimum here, I will call this p star, and this is a d star, the dual one. So and they are actually equal under very weak conditions. And the point is, we don't know them, right? We don't know the perfect solution, but we know that it's between any primal value we have and the dual value we have. So that's why this is called a certificate. So okay, you have any x, you have any u, and you know that the truth is somewhere in between, but you don't know the truth. So that's useful because in deep learning problems you usually don't have that, but because these problems here are usually convex, especially in the examples here which are listed here, regression, classification, and so on, as we discussed, this stuff is convex. And if you have convexity plus a very weak condition on these f and g's that are kind of well behaved and convex, then you have that this stuff is equal, that the optimum of the primal and the dual solutions are equal. And the approximations you have, of course, the primal one is higher and the dual one is lower than this magic unknown value. Therefore, the difference of the dual value you have and the primal value you have, this difference, this gap, so the gap between what you have here and the gap here, so this gap you can use as a stopping criterion. So you can say if that's below a certain tolerance value, epsilon, or which is given by the user, if that's small enough, then you can say, okay, I'm happy, I stop my solver. I have to guarantee that the true optimum here, which is unknown, but I have to guarantee that this optimal stuff is between the two values I have now. So this is the optimal one. So. All right, this is very useful. And this will allow us to stop our solvers and give a guarantee, because this is very important. If something does not work in machine learning, you don't know why it doesn't work. You don't know, maybe you choose the wrong model or the wrong regularizer or whatnot. At least here, you know, it's not the fault of the training. The optimization, the training that you know if it works or not, because you can look at the duality gap. So, okay, that's an advantage. Unfortunately, we do not have this for deep learning, because there we do not have convexity. All right, this is all I wanted to say about duality. So now, in the second part, we go to something completely different, which is a much more general class of problems and optimizers, which is zero-order optimization. So what can we do if we do not even have gradients? Can we do optimization? So if we just have function values, can we optimize general functions? So this is called gradient-free, it's called derivative-free, it's called black box optimization in some cases, and it's actually something even more general, right? Because you can apply to any function f you want. And what I'm going to show you is that it's also quite a natural thing, and it's quite related to some of the stuff we have seen on gradient descent. But here this will allow us to apply optimization even more broadly to some problems which are not differentiable and we know almost nothing about the problem. So that's the question. Can we minimize a function if we do not have gradients? So here's the problem we want to solve, just standard minimize f of x, but no gradients around. Can we do it? So here is the method, and it's basically quite a naive method. You just have, it's just random search. What you do is, okay, I'm at x currently, I walk in a random direction in space from my current x. I'm at xt, I'm going to pick a random direction from all d dimensions, so not only the coordinate directions, but really here I mean any direction. So you take the entire sphere around you in d dimensions, pick that sphere, pick any direction in that sphere. Well, it doesn't, okay, here it doesn't even matter if it's a short or long vector. Pick any vector you want in d dimensions. And then walk in the direction of that vector. So that's here. And how far should I walk? That is the tricky part. So this thing will only work if I'm careful how far I walk into the vector. Also, there are actually, once you have decided on this random direction, there's two possibilities. Either when you walk in the direction, your function value gets better or it gets worse. So if it gets better, you're good, you can use a positive lambda. But the other possibility is just it gets worse. So then you actually should walk in the opposite direction. So then that's why we have this lambda here, the step size, which allows us to do that. If d is a bad direction, goes uphill, then I will just use a negative lambda, so I will walk downhill in the end. That's our goal. So the trick here is to use this line search. So, and I mean, this is not cheap, right? This is it's going to be tricky. We get back to that. But if you have this kind of oracle which tells you if you should go forward or backward and how much, here we just say we take the best one, which improves our function the best on this line. If you have that, then this seems a reasonable algorithm, and then you can use this gamma to perform your step in this any random direction. Okay, looks quite simple. It is actually, takes 2 lines to implement in Python if you have the line search by some oracle. Well, okay, this is actually also pretty simple to implement. Just the question is how efficient is the line search. Anyway, super simple algorithm, and on the next slide I'm going to also show you that this thing actually works. Probably it works almost as good as gradient descent, but there is kind of a huge slowdown from the dimension, which we're going to discuss. Okay. Here's what we're going to prove. We're going to prove that this thing converges the same as gradient descent. That sounds crazy, because it's such a simple algorithm. It doesn't use gradient, it just uses a random direction. So I'm going to show you it has the same rate as gradient descent if you have smooth functions. And the proof I'm going to show you is showing you that it will work for convex functions. And let's see. So you know how to optimize smooth functions. You have seen this a million times. What you have usually done when you had this L smooth function, convex or not, whatever, you were using the sufficient decrease property. You were saying that, okay, if I walk in the gradient direction and I use a step size 1 or L, then I get an improvement, provably. So and I can also not overshoot, so I really improve my function value. So the picture is maybe looking something like this. So here's your f, but you don't see the whole f, right? You only you don't have gradients. So you're currently at x. So what do? You want to go down here, right? So you want to here walk in the left direction, and maybe so maybe this was d, the random direction you chose, or maybe, okay, let's say this is the d direction, but then here gamma would tell you that, okay, you should, d sounds stupid because it goes uphill, therefore you should use a negative gamma, so so you want to walk in the left direction. That's just an example. Okay, so mathematically, what happens? So this is what happens. Because that is straightforward just from the definition of smoothness. Smoothness means, remember, it means that you are below a quadratic. So it's super easy. You take your Taylor expansion of f at x, so the linearization at x, that's what we have here, sorry. So Taylor expansion at x, okay, I'm messing up the colors. This is the linearization, f of x plus the gradient. And then the question is just, so what's my new point? Of course, my new point is x plus d, the step size. So from the linearization, I have this term. And then from smoothness, I have that I'm below the quadratic of how far have I moved. How far have I moved away from my x? And that's exactly d times gamma. So d times gamma squared is how far I've moved in square norm. All right, this we have for sure. And now the question is, when is this an improvement? I mean, it's still not clear if this thing on the right-hand side is better or worse than the original value on the left. So if we had sufficient decrease, then we had that this thing, actually the term here was negative, so then we got an improvement. And now it's not so clear if the term here, the linear term plus d, is negative, and that's what we have to talk about, and that will depend a bit how well this d direction is aligned with the gradient, and that's what the middle term here is doing. So let's see. What we are going to do is we do this a bit abstractly. So we say that there would be a perfect step size such that this would improve the right-hand side. It would make the right-hand side better than the original value. And that's this magical step size here, which we call gamma bar. The claim here is there is a gamma bar which minimizes this right-hand side. So I just take the best gamma from this perspective, so which makes this thing smallest. It's not the one we use in the algorithm. In the algorithm, we use a gamma which is directly minimizing f. But here I'm talking about a hypothetical gamma bar, which minimizes this right-hand side. And okay, it's very easy to minimize this thing here. You just set the gamma derivative to 0. You know how this works, so I mean gamma is just a number, so you just optimize this to be smallest, which means you find a gamma which balances the two terms, which is this inner product here and the squared norm here. So you know that what the best solution for gamma is. If you plug it in, you also know what the value is that this gamma achieves. So that's the standard trick. So there is a theoretical gamma which makes this smallest, and smallest means this. And the cool thing about this is that this is negative. So now this is a strict improvement. That's cool. So there is a minus here. So we have achieved what we wanted. And this will remind you of sufficient degrees, right? So sufficient degrees just had kind of the gradient norm squared and the L. This is a bit different here, but the point is that this is squared, so this is a positive term and it has a minus in front of it. So if you, for example, if you happen to be lucky and the direction D happens to just be exactly the gradient, then you would actually get sufficient degrees, basically. But the nice thing here is that even for any other D, no matter what it is, because we have chosen this perfect gamma bar, whatever it is, this thing is going to be a positive term, and that's going to be the term which is improving your function value, so get a strict improvement in every step. If this thing here is bigger than 0, which it is, it's a square, right? I mean, it could be equal to 0, yes, but it's non-negative, so you improve. For sure you will not get worse. So, and the improvement is exactly this quantity here, which now happens to be an inner product squared. Okay, this sounds interesting, and I'm telling you, it's very similar to sufficient degrees, but it's a bit a smaller quantity than the one you get from sufficient degrees, because sufficient degrees only holds for the true gradient direction, and here we're not using the true gradient direction, we're using a random direction D. So this is what you would get for this hypothetical gamma bar, but now I'm saying just the one which I actually took is going to be better than this one. Why? So here's the one from gamma bar, which is just said it's going to be this strict improvement, which is nice. The one I actually took is the one here, gamma. So that's step size we actually took. That one is better because we have chosen this to minimize the f itself. So that's why you have this inequality. Okay, so what we now have is that the new value is smaller than this thing here, and that is strictly better than the old thing, which is the old value of xt. So we're done, we have a convergence rate, basically. If we can explain a bit better what this thing is in expectation. That looks a bit strange, so I take a random direction, I ask what is its inner product with the gradient. So it's just the inner product of D, the direction D with the gradient, its normalized direction. I think I have a typo here that this needs to be, there's no square here. Okay, I'm asking how much is my random direction aligned with the gradient, and that's my improvement. Now, to get this, this is super easy if you have this if you know what a random direction does in the Euclidean space. Sorry, so this is what I'm talking about here. So this itself looks a bit scary. So but what it's saying is that, okay, we have a given direction G, it's fixed. So the role of that is the gradient, which we don't know anyway, but it's fixed. So that's G. Now you're taking a completely random direction, which is called R, and you ask, how much is a completely random direction aligned with a fixed direction in the space? And that's depending on the space, right? So if you do this in one dimension, you get this value. If you do it in 2 dimensions, it's going to be a bit of a different alignment. But this is known, so just the fact how much is a random direction aligned with a fixed one, that thing is super well known. And this is a little lemma, so I'm not going to prove it here. But this is 1 over d times 1, basically. So assume that G is a unit vector. So how much is the random R vector aligned with that fixed unit vector? The answer is 1 over d. So if we have that little lemma, then we can easily finish our proof, and here it is. So this allows us to go from this quantity here, which is a bit strange, but what it is a random direction aligned with our gradient. and we ask how much is that random direction aligned with the gradient squared, and that's what we have in the lemma here, so that stuff is correct. So when we say that this in expectation, because d is random, so in expectation this is 1 over d times the norm of the gradient, and that's exactly what I put here, 1 over d times the gradient norm. So we're done. And the gradient norm squared, that's exactly what you had in sufficient degrees. So it's the same as we know already. So the same result as we get in gradient descent. 1 over L times the gradient norm squared, that's exactly sufficient degrees, except there's now the 1 over D. So that's terrible. So this is a terrible slowdown. I mean, D in real applications is 1,000,000, so stuff is 1,000,000 times slower, but the rate is basically exactly the same mass, which leads to this rate, and we can understand it exactly the same way as we have understood sufficient degrees, which was for the gradient-based optimization. Now we can get a very similar result, basically the same result but multiplied by D, it's a D times worse, for random search, which is quite nice. So even without gradient, we can very much benefit from our understanding of gradient methods. This is for convex, but you have already seen that the sufficient degrees holds for non-convex optimization as well. So you already know that this same thing you can also get for non-convex function, but then you have that you just go to a stationary point. You can make the gradient small in so and so many iterations, we know this. So the same thing you now also have for gradient free, which is quite nice. Okay, so we understand how gradient free random search converges, and we were able to use our same theory. Okay, so it is actually quite an important argument in practice, because in practice many times you actually do not have gradients, and this is the only thing you can do then basically. And it's probably nice that we also understand how it converges and also how it depends on how many variables you have. So this D, the number of variables, here has a huge influence, so it's D times slower. Whereas if you have gradients, then the D doesn't matter basically, because we saw the only thing that matters is this L, the smoothness constant. There was no D if you have gradients, but here there is a D. And that's summarized again here, so same rate, but slowdown of D. It's not so hard to actually extend this a bit more. That's basically what I also said before. So you can get the usual rates that we already had. You got them for convex functions, say, now we got it for gradient free, which is just that's what we have shown on the previous slide. You can also do this with strongly convex and smooth, and then you have the same rate. The geometric fast conversions, remember, the logarithm, 1 over epsilon. These many steps were enough to get a epsilon approximate solution with gradient descent on strongly convex and smooth. Now we get the same thing, but with a slowdown of D, so that you can also show. And as I said before, even for non-convex, you could make this exercise and ask how well does gradient free do for that case. Alright, so it works, but it's slower, and yeah, in practice you actually do observe this slowdown with D. So it really depends what you optimize. In some applications you only have a few parameters, and then this can be very good methods. So think of like hyperparameter tuning, because that's, you don't know, finding a function value is expensive, so you have to see how you do the line search actually. Sometimes people just skip that line search and do some tricks instead. If you're lucky, you will still get descent. Or you just do basically what that then boils to is basically the same as grid search. Can be some smarter version of grid search. Grid search means I just take a grid of function points and I'll check my function value at every point. And that of course is very related to what we're doing here. And so if you have D small, then this is an excellent class of algorithms. If D is large, like the parameters of a neural network, then you don't want to pay this slowdown of 1 million. So, but this is a very interesting class of functions and methods to optimize them. All right, applications. I mentioned already hyperparameter tuning, which you have here. So sometimes you have like discrete optimization problems where the X space is discrete. So then our theory doesn't apply, but the method is perfectly applicable. You just pick a random next candidate and check if the function value is better than before. What's also interesting for some of the research we do in our lab is to ask about memory and communication advantages. So if you do this on many computers, these methods can also be attractive because you don't need to send and exchange the gradients to form a mini batch together, but you only need to exchange function values. So if you do this with many participants, you just need to exchange who has the best f value, and that's the one you go. So that can be an advantage, but it's not clear if that really is enough to beat gradient methods. It's definitely a very important method in reinforcement learning. So there, it's probably the simplest method you can do to just do this kind of random search and see how much of a reward you get. So I'm gonna get back to that on the next slide a bit. Also, these models that I just presented you, they can be again extended using ideas we have seen in the course. So for example, what we just did now is basically we use these random directions to imitate what happens in gradient descent. So you can say, okay, if I have second order information, if I have the Hessian or second derivative, then we know that we can get even faster conversions, which was Newton's method. There is a nice analog here so what we're doing here is we kind of learn a first order model here, even if you do not have gradients. So what you can do here is you can do the same kind of tricks to actually learn even something about the second order approximation to your function, also, which is called the curvature. And you can do that based purely on the function values without ever seeing gradients. And that is also a popular class of methods which are analyzed in the literature. For example, these are called like CMA covariance adaptation. So it's an evolutionary. So this kind of evolutionary search. So random search and evolutionary algorithms. It's basically the same thing. So it's kind of a funny story that this evolutionary algorithms always sounds like super catchy, that people think it's a interesting concept that we kind of can learn good candidates of these random directions. So evolutionary algorithms are basically just that. They're derivative-free search algorithms, and they're random search algorithms, which is really, really close to what you have seen now. And what I'm saying as a practitioner is it doesn't matter so much if it actually is evolving or not. What really matters is that the random search. So the random search, the plain old random search already works well, and the rest is just going to get slight improvements. So the big problem is that we have this gigantic dimension D, and that is inherent in random search. There are even lower bounds that you cannot avoid it, and that we have seen why that comes in when we studied the proof on the previous slide. And this is not magically going away with evolutionary algorithms, though in some settings you can be lucky that you are able to figure out a subspace or kind of a better model to your function to then stick to that model in the random search, and that's, for example, what these second order models can help doing. So, all right, random search is pretty competitive, even for reinforcement learning. Sounds disappointing, but true. But it's also important to always use this as a baseline, and well, it's also kind of encouraging practice that you can get often good results already with random search. So what actually is reinforcement learning? I won't spend so much time on it because it's not the focus of our course. but just so you have a brief intuition of what it is. It's very simple actually, just a bit of a notation mess. So what it works is that you have a system, for example, there is a car which has to drive left or right, and there is an environment. So the car and the environment together, they're the state, so they're in some state. The car is at that position. Now you can, so that's the state, S. Now you can take action, so your car is here. You have to take action, you either go left or right, and then you also have some nasty noise. And then what F is, that's basically nature. So F is just gonna tell you that if you take this action going left in this state of nature S, then your next state is gonna be t plus 1, you will have crashed into the wall. So that's st plus 1. And now what you do, of course, the question for you is how to do good actions. So to find the action based on the current state, so and the previous states, to decide what is the best action to take. Let's call this policy here. And so now we have to find which is our best discrete action. So A is discrete, so don't be confused with that. So A is just always, at every time you can go either left or right, for example. It can be continuous, but it doesn't have to be. Now if you do this, then after a while you get a reward. So you play this action A every step, and then after a while, depending on what actions you took, you get a reward, which is called R. So that's going to be like that. So you want to maximize this. You want to find the best action such that the reward is maximized over the time. Of course, you have to respect nature, that if you do this, the next thing will happen. Okay, so it sounds like a pretty hard problem, especially because it's hard to get gradients here. I mean, there are methods which get gradients here, but it's very tricky. So these are like policy gradient methods, for example. So it turns out that the gradients you have are quite difficult to estimate. So then, of course, you would say, okay, I can do an even simpler method. I can just throw a random search at this. I will just do a random search or this finding a good finding a good policy, and see which one gets the highest reward. And that's always a nice baseline to use, and in many applications performs quite decent. Okay, and there are different. Reinforcement learning is called a very big topic. What's hard is that there's this kind of disconnect. It takes a while. You do many actions, and only later you get a reward. So it becomes very difficult to have a continuous dependency. Very difficult to find a gradient on how these actions you took really influenced the reward. You only got 100 steps later in the game when you died from the other player or whatever. So that's why these problems are very hard, and to optimize them are also very hard, and that's why random search is a suitable algorithm. So because that always works, except might be very slow. Okay, so that's what we can do without gradients. And as a very last chapter today, I want to tell you a bit more what you can do with gradients. Because in standard deep learning, we actually do have gradients. So basically everything with neural networks, supervised, unsupervised learning, most deep learning applications are driven by backpropagation, and backpropagation is nothing else than computing the gradient. So we have gradients, why not use them? And so this chapter is to give you a bit an overview of what are the training algorithms the optimizers use for modern deep learning methods. And that's what we want to talk about. And it's mostly stochastic gradient descent, actually. It's quite surprising, but that's also again encouraging, because that's one of our main focus in the course was to understand the SGD, and this is going to be super useful for deep learning. And it's quite fascinating that because deep learning has been around for so many decades, and still SGD is still one of the best algorithms. And what I'm going to show you now is that while that's still the case, there are slight variations of SGD which actually are able to outperform SGD in practice. In theory, this is not completely understood to all details, but maybe even we have some convex convergence rate where we can understand that this variant would behave a bit different from the other SGD variant. But I'm going to show you the algorithms first, and then we can discuss a bit more. So, but this is opportunity for you to recap SGD. Make sure you have that present, because now we're going to modify it a bit. So everything in deep learning is this finite sum structure. Sum structured objective means you just have a bunch of training data points, and then you want to minimize the sum of the loss functions. So for every data point is a loss, right? So this is the loss over data points. That's the problem we minimize. So we minimize f. That is training of a deep net, say, and x are the parameters of your neural network. So you have networks have like millions of parameters or billions, gets larger and larger, and in neural networks it's very common to have more parameters than data points. That's completely fine. So x are the weights or params in as many parameters as you have, d dimensions, and d is really billions or so, even if you might have a bit less data points. So okay, so that's the problem we want to do, and you know what SGD does on this. So SGD, so yeah, forget about this for a second. So what SGD would do is this, basically. So SGD would just take a stochastic gradient. What is that? That's just a gradient of one of the FIs. That's a stochastic gradient. So we sample a batch of data points, a mini batch, just one data point for simplicity. You sample a data point, compute the gradient of Fi, of the data point data point j. So you have that gradient which you call g, and then you just apply it to all your parameters. So here I write this per parameter, so you just apply the g, the gradient, to every parameter. So of course there is, for every parameter, for every weight of the neural net, it has its own gradient entry. Okay, but this slide is not on SGD, this slide is on, so okay, I can still maybe show this here. So this would be SGD. So this slide is on a variant of SGD which is called Adagrad. So Adagrad is, when was it, like a few years ago? Was proposed as a very performant variant of SGD. It was originally proposed a bit with a motivation of a second order kind of motivation, that in front of your gradient you put something which depends on kind of second order information, and that is the stuff which we have here. So that stuff is kind of mimicking second order information, and you always put that in front of your gradient before you do your step. Now, what is it? So the variant of SGD of Adagrad which is used in practice is this one here, and that means that the G thing, capital G, is just it's just a diagonal matrix, basically. So it's a very simple kind of second order information, and it just tries to give you a better learning rate for each coordinate. So, and what it is, this G is just a rescaling. So you have I is going over all these dimensions, right? So for every dimension, every parameter, you have its own learning rate. That's basically what this capital G is doing. How it's defined is quite simple as well. It's just summing up the gradients over the past for that same coordinate. So what it's doing is I'm just asking, what is a good learning rate for my first coordinate, which is the one of the weights in my neural net? And what this stuff is saying here in undergrad is saying that you should use the old gradients you had for that weight. So x is the weights, right? And then so we just look at one of the weights. This is the weight xi. It's the weight of that edge in the neural network connecting two neurons, and there are billions of them. And for each of them, I will construct and accumulate a special learning rate to make some of the weights take a bit larger steps and some a bit smaller steps compared to or relative to the gradient I have on that edge. Right, the gradient in every step will influence all the edges of the neural net. So if you get, what you do is you feed in data on the bottom, you get out an answer at the top, get a loss, you backpropagate, and then the gradient tells you that every edge of the neural net should be changed by what? By this G I of the edge, of the ith edge. So it should either increase or decrease that weight of that edge. That's what the gradient is. That's what the stochastic gradient tells you. And usually you just apply this with step size gamma, but because we are adaptive now, this is autograd modification, we have also accumulated on this same red edge, we have accumulated how big were the path gradients. And what we have done is we have summed up the squares over all the path gradients for that same edge. We keep track for them, and we sum up all the squares of these gradient entries. So Gi is just a number, right? It's the gradient of just that single edge. So that stuff is summed up, and it's done separately for every edge, right? So just the squares are summed up over the time. So from now to the past, it's summed up. And then before I apply my actual gradient on that edge, I will pre-multiply it by the square root of this sum. And you actually divide by it. So that's what autograd is, or the diagonal variant of autograd. So what that does, the effect of this is that if you had very gigantic changes in the past on that weight, xi, then you will be a bit more conservative in the future, because if these were very big, then they sum up to a big number, so then you will divide by something big. So that makes you will move a bit slower in the future, because you got a bit scared because changes are gigantic. Therefore, you will be a bit more conservative with applying gradients on the edge. And on the other hand, if your gradients were always very small, so you had the edge of your neural net was not changing much, the weight was on that edge here was always almost the same. So then I can become more aggressive. Then I have a small sum of path changes. So then I have a more aggressive step size because I will divide by a small value of this sum over the past. That's the idea. And surprisingly, this works super well. It's kind of an adaptive or coordinate-wise learning rate. And this performs well, gives you a faster convergence in the training error. So the loss, so F is the training error, right? The loss of your training data points goes down a bit more fast in practice. But it's sometimes for the test accuracy, people observe that it's not necessarily better than SGD. But that depends a bit on the kind of neural network you use, the kind of data set. So this is a bit of more engineering discipline than a science, but also very interesting and motivating to actually try to theoretically explain why some method works better in test accuracy, or it generalizes better than another method. Because in the end, we kind of have to look at this everything together. It's not just a neural network, right? Why it works well on your test set, it's a neural network combined with the optimization algorithm. These two together, they generalize nicely. They give a good test error. And SGD does very well on that. So it generalizes super nicely. And this one is a speed up for training. So you can do that. And if you want to implement this, the overhead is negligible. It's almost no cost. So remember, this is deep learning. We can completely forget to think about a full Hessian or second order information. We could never store a matrix which is like squared in D. But what we have to additionally store here is just linear in D. So we just have this one additional vector, so as D, one entry per weight, which we have as additional memory here. So yeah, if the model are big, then so SGD needs no memory, just needs the X and no additional memory. And this one has an additional memory of the size of one model. So, but that's okay. But if your DeepNet already fills the GPU completely and you can just store the gradient once, then you will not have space to run AutoGrad. But if your model has space to fit twice two of the models on the GPU, then you're good, you can run AutoGrad. Same as Adam, actually. So next slide is about Adam, which is basically the same thing. So Adam is another small modification of this. Two others are Adam, Auto Delta, and RMS Prop. They have basically the same intuition as I just explained. So here is Adam. It's really the same thing as AutoGrad, basically. So you might be a bit scared why it looks so different. So what's happening here is this V stuff. That is what we had before. So the V is, again, it's just accumulating this what we had called capital G on this slide here, which is a sum over the past of all the gradients entry on edge I. That's the same thing with VI. The difference here is that we have a bit of a faster decay now. Now we have this exponential decay. So that the more recent G will count more. So beta is so this is just, at every time V stores these statistics from the past, and at every time you forget it, so the old V, you kind of forget it with this vector B2, and you add the new one. So that's why this is kind of an exponential decay, and here we just had the sum of everybody weighted equally. But here you give more weight to the most recent ones, and the old ones will get multiplied by B2, so they will decay quickly. Okay, so that's the story about the V's. That's kind of the same as before. Now there is something else happening here with the gradients, and that's what's called momentum. So that's the M. Because traditionally you would just here apply the gradient that we had before in SGD and also in the AutoGrad. Here we apply a slightly modified version of the gradient. It's very simple. It's this here. It's again accumulating the old gradients plus some bit of the new gradient. And that is momentum. So momentum, we discussed this when we did acceleration. So you had this in lecture 6. So when we said that was actually for full gradient methods, we saw that it's actually an excellent idea to not completely forget the old gradients, but to keep moving a bit into their direction. So to accumulate the sum of the old gradients and keep pushing a bit into that direction as well. And that's exactly what we are also doing here. It's the same thing. So we have momentum is accumulating the old gradients G, and there is again a kind of an exponential decay here, which seems nice. And here there's a decay factor, which is called beta 1. So that steers how much weight to give to the new gradient and how much if you have a very long beta 1 is close to 1, then that means that the old gradients still have a lot of influence. They keep pushing in the same direction. So momentum is actually super important in deep learning. Without it, you cannot get a state-of-the-art accuracy in most, for example, image classification settings, except if you're like super careful to tune the step size. So momentum is quite important, and what we have here, so Adam is just these two things. It's a coordinate-wise learning rate, which just discussed before. That's what he gets from undergrad. That's the blue stuff, the second line here. And it has momentum, that's the green line. So that's Adam. And that is the kind of state-of-the-art algorithm for at the moment for all NLP methods, which are based on this transformer or self-attention networks. So self-attention is a very nice type of a layer you can have in a neural network. It's very simple, just 3 matrices multiplied together. It allows the network to choose its own combination of different input elements in that layer. So this is quite popular in natural language processing, and it can also be seen as a kind of a generalization of CNNs as well. And these work quite well. And to train, these are also very big, so they have lots of parameters. So to train them, most people prefer Adam. So it's kind of faster than SGD. Why is that? It's not so clear. So this is a big discussion. So because SGD can almost always also get the best possible test accuracy. But what people do not like about SGD is that it's very sensitive to which step size you choose. So that is always something that has to be kept in mind. So that's probably the main advantage of all these algorithms which you discuss here, which is undergrad and Adam. That why they're so popular is mostly that they are much less sensitive to this gamma step size. In SGD, you have to do this very carefully to get the best performance. And here, because you have coordinate-wise learning rates, there is an effect that the algorithm itself adapts to a rather good learning rate no matter what initial gamma you took. So it's a bit less tedious to find a good learning rate, finding a good gamma. Right? And if training takes 1 week to have one training, then this is important, right? It's important that they'll have to try 10 different values for gamma in SGD, for example. It just costs real money, right? I have to train 10 times instead of 1 time. And here, if I just use Adam, the hope is that maybe I only need to try like 1 or 2 or 3 parameters, because it turns out that the default parameters, beta 1, beta 2, and gamma, they do pretty well. So you can have some hope that this might be converging at a better speed, at a good speed, without much tuning. Whereas if you want the very, very best speed, then again you have to do many trials for what's the best beta, what's the best gamma. Okay, but the idea that you have a learning rate which adapts to every weight is very interesting, and also relates a bit to the curvature you might have in all these. Each weight I in the neural network might not have the same importance, so each coordinate from an optimization view is each coordinate of your problem might have a bit of a different curvature or different smoothness and all these things. So that's something which seems to be a good idea, to have an algorithm which is adaptive to this, which is adaptive to how well does each coordinate respond to these gradient steps. So that's basically it, what I wanted to say about deep learning algorithms. So these are 2 very important variants of SGD, undergrad and Adam. So, and the overhead they get is basically nothing, so here you just need to store actually 1 or 2 more vectors, so it's quite efficient. Because the main cost anyway is to compute the G, the stochastic gradient. That's a costly thing, the rest is just adding 2 vectors and that's it. There's a memory cost too. Okay, the very last thing is another variant which looks much simpler than before, but it's actually very related to what we discussed. So Adam turns out, looks quite complicated, but it turns out it is very similar to this thing here, which is called sine SGD. And this thing is super simple, so much easier than the ones before. So what it is it takes the stochastic gradient, and then it completely forgets the magnitude. It will just use the sign of each coordinate of the gradient. So it's either +1 or -1. So it doesn't care at all about the magnitude of that thing. You would just use the sign. And it's quite surprising that this actually works quite okay. In practice, you can get this to work. You might have to use a learning rate, which is scaling a bit with the norm, so that the overall magnitude of the entire vector is kind of okay. But then for each entry, they're just +/-1. So, okay, so this seems quite surprising. It's also, it does have some useful side effects. So now the gradients are big, right? The gradients are usually as big as the model. You have 1 million parameters or 1 billion, and each one of these is a float 32. So there's a big memory, every gradient is big. If you are doing this for distributed learning, you know, 2 people contributing to the training, they need to send their gradients and add them each round. It's very expensive to send so much data, which is exactly as much as the model X itself. So here it's cheaper. Here you would just send a vector of +/-1s and maybe the norm if you want to scale up the gamma step size. So you need to send 32 times less data, which is kind of nice, for just a bit instead of a float. So that can be nice if you have distributed learning. And this argument is also a bit related that it says that the magnitude of G doesn't matter much. What really matters is the sign. And that is a bit related to Adam. If you look at here, you see that, so M is basically the gradient. On the last line, it's get divided by V, M divided by V. And V is basically the magnitude of the gradient. So you see here the magnitude of the current gradient is already taken care of. So if you would say, forget about the old guys, just look at the current guy, well, that would mean I will divide the current gradient by its magnitude, and also forget about the momentum. So then you have that this update is doing a bit something similar as just taking the current gradient but ignoring its coordinate magnitude and just basically applying its sign, right? If you take M divided by its magnitude, what you get is the sign. So this is a bit related if you would only use the current one for a special decay factor. Okay, so that's interesting and can have some practical applications. Turns out it's actually wrong as an algorithm. Yeah, that's actually interesting. Both Adam and SignSG are wrong in the sense that they do have problems to converge on convex. There is some special crafted convex problems where you can prove that these algorithms will not work. Both Adam will fail and SignSG will fail. And that small observation that there is a catch that you need to be a bit more careful with these algorithms, that was actually a best paper award in, I think, ICML on Europe's last year. The fact that Adam has to be fixed, otherwise it can be a diverging algorithm, but that actually was fixed and it's not so hard to fix. It just has to do with a very slight modification. You have to also make sure you correct correctly for the initialization. Anyway, but it's important to keep in mind that to understand these algorithms, you need to understand them on convex functions. That's how people actually then found this problem, and that's also what you would do to understand how fast is this algorithm, because you will give a rate for its convergence. And the same for SignSG. There are some examples where it doesn't work, but in practice, surprisingly, it does work quite often. All right, that's it for today about deep learning. And next week we will discuss a bit more about practical aspects of optimization. Okay.